Welcome to example number 6, which looks at the basic principles of a mass spectrometer. Now, a mass spectrometer is an instrument that measures the masses of ions, which are charged atoms or molecules, and thus it measures their atomic and molecular weights. Let's take a look at an animation of a mass spectrometer. In one type of mass spectrometer, the atoms or molecules are first ionized, so they're charged positively. The ions are fired into this region called the velocity selector. In the velocity selector, we have two crossed electric and magnetic fields. So we'll introduce an electric field going upwards in here, and then a magnetic field going out of the screen. And let's fire our charged particle through here, and you can see it's following a nice straight path. The velocity of this charged particle, if it makes it right through this region right here, we found out in the earlier problem to be equal to V equals E all over the magnetic field. So the ratio of the electric field to the magnetic field. The faster particles won't make it through because they'll curve this way because of the stronger magnetic field pointing downwards. And the slower particles will curve the other way and not make it through because of the stronger electric field. So the velocity selector really only selects particles with exactly this velocity, which is equal to the ratio of the electric field to the magnetic field. Next, the beam of ions enter a region with a second magnetic field, pointing typically in the same direction as this one, but a different strength. If you notice, the beam is now following this nice circular path right here. Particles of different mass will have different radii, so that you'll see that they'll separate essentially different charged particles. If all charged particles have the same mass, then they'll follow the same radius. Well, back to our example. This is slightly different. This mass spectrometer, instead of using a velocity selector, uses a fixed potential difference with this parallel plate capacitor. So the particles start from rest and are accelerated instead of using a velocity selector with crossed electric and magnetic fields. If all the ions have the same charge Q, then they'll all have the same kinetic energy when they enter this magnetic field. And if they all have the same mass, then they'll all follow this same arc path. Okay, let's tackle part A. Let's determine the velocity of that charged particle as it reaches this point B. So, what do we use to solve this? Hopefully you're remembering I talked about kinetic energy. So, where did it get its kinetic energy? There's a change in kinetic energy. Hopefully you're thinking, well, it must have been from the electric potential energy. Now, the electric potential energy is really equal to that change in electric potential energy is equal to Q times the change in potential or voltage. So Q times delta V is equal to 1/2 mV squared. You'll notice I'm using a capital V for voltage and a small v for the velocity. Now this is the velocity at point B here. And so this change in potential, you can think of it as the final potential minus the initial potential. So this is really VA minus VB is equal to 1/2 mV squared. And we can see that potential difference is 2100 volts. And we have the charge is a proton. So Q is a proton, which is 1.6 times 10 to the power negative 19. That's the charge of a proton. The potential difference is 2100 volts, which is really joules per coulomb. And this is equal to 1/2 times the mass of a proton, which is 1.67 times 10 to the power of negative 27 kilograms, times the velocity v squared. And rearranging and plugging this into your calculator, I get an answer of 634,346 meters per second, which is really the same answer we have down here. Okay, so now we know how fast this beam is coming in here. Remember, as it's traveling here, it's going to continue with the same velocity. Why? Because the force is acting perpendicular to this, and that's not going to cause it to change its speed. It's going to change its direction only. So now we're going on to part B, and so this is a circular motion problem. Remember, centripetal acceleration. So now we're going to apply Newton's second law, sum of F equals ma. But this acceleration that it's exhibiting is a centripetal acceleration, so this is AC. If you recall, you can rewrite this side as mv squared over r, which is the radius of this orbit as it goes around here. And the force that's responsible for causing it to go in this circular path is the magnetic force. The magnetic force, hopefully you recall, is Q times V times B. That's the velocity it has all the way through here, B, times sine of the angle between the magnetic field, which is out of the page, and the velocity is along the plane of the page, which is 90 degrees. So this is just going to cancel out to be 1, which is equal to mvb squared all over r. Now we can do some cancellations here. Now let's rearrange for r, getting the following expression, and then let's substitute in now. And oops, I just realized that I actually forgot to give you one very important piece of information here. I don't know the magnetic field. We wouldn't be able to solve this if we don't know what the B field is. So I'm just going to do a quick little calculation, work backwards, and try to figure out what would be B if I knew what the radius was this. And it turns out that B should be 0.1 Teslas. And so our final answer, R, is equal to 0.066 meters as shown below. And that's it for this example. And I'll just add in this little note here.